Okay, let's get started. Hi, everyone. Welcome. This is the last webinar in our three-part series that we've called Research to Action for Resilient Agriculture. We're really happy that you're joining us today for the session on balancing small-scale irrigation solutions with sustainable groundwater use. My name is Jenna. I'm a program manager with the agriculture sector at the Center for Effective Global Action, or CEGA, which is based at UC Berkeley. We're fortunate today to have two distinguished speakers and researchers joining us who will share their research on groundwater management. Both of these researchers have worked extensively on these issues across the globe, and today the projects that are in focus take place in Gujarat, India, which, as you may know, is a hotspot for water scarcity, which of course threatens the long-term sustainability of agriculture and livelihoods in the region. Before we dive into today's presentations, I have a very brief introduction to CEGA's agriculture program. We co-manage two agricultural initiatives with the Abdul Latif Jameel Poverty Action Lab, or JPAL. Together, our mission is to generate rigorous evidence to test new ideas that promote farmers' use of agricultural technologies, help them manage their risks, and better link them to markets, ultimately boosting their profits. In recent years, our research portfolio has incorporated more work at the nexus of climate and agriculture, recognizing the threats that unsustainable resource use poses to global food security and livelihoods. Both of the studies that we're going to look at today were supported in some part by these initiatives. And I should note that the Gates Foundation and the Foreign Commonwealth Development Office have provided funding for the initiatives that funded these projects. So before we dive in, a few very quick housekeeping items. First, we have 60 minutes for two presentations, and we'll hold an open question and answer with the audience after both presentations are complete. You can use the Q&A feature to submit your questions throughout the session. We'll address as many as we can at the end. This webinar will be recorded, and I'll distribute the link after the webinar sometime next week. With that context, let's dive into today's presentations. First up, we have Ram Fishman. Ram is a professor at the Department of Public Policy at Tel Aviv University, where he directs a sustainable development lab. Ram is a development and environmental economist whose research is focused on sustainable agriculture, water scarcity, and climate change. Ram holds a PhD in sustainable development from Columbia University and is currently an economics fellow at the Center for Advanced Studies in Behavioral Sciences at Stanford University. With that, I will turn it over to Ram to get us started. Ram, would you like to share your screen?
Yes, sure. Thank you. I hope that this is visible in full screen.
Looks good.
Okay. Hi, everyone. Thanks, Jenna. Thank you, CEGA. Thank you, JPAL, for supporting this work. So I want to basically discuss a little bit some ideas about how we can bring smallholder irrigation towards a more efficient situation and what are some of the challenges that we've been encountering in trying to do that. So just to start off at a very big level, we know that in many parts of the world, water is becoming more and more scarce. We know also that irrigation is the number one user in terms of quantity, and we know that often irrigation practice is inefficient. Water is not allocated efficiently. There are technical forms of waste and inefficiency as well. And as we try to sustain irrigation, as we become more concerned about sustaining the availability of freshwater resources, obviously one of the ways to deal with that is to use the resource more efficiently in order to conserve it. So that's a very large challenge, and it affects many parts of the world. And as we think about it as economists, maybe, and not just economists, but economists, agronomists, engineers, how do we envision what would it take to move the current irrigation economy in all over the world from something like you see on the left, where water is kind of just pumped out into fields through open channels without any monitoring, etc., into something that maybe looks a little bit more like what we have on the right, which is actually something we did in our field site in Punjab to actually start to install meters, more robust piping systems, et cetera, and of course to also incentivize farmers to do it more efficiently. Where I come from in Israel, every drop of water is metered, thought about, used very efficiently, but that is not a representative part. That is not a representative of the rest of the world. So let's think about what we could do and whether it's feasible to try and get there. So again, in broad form, if we think about how do we move farmers, irrigators towards a more efficient water economy, a natural way to think about it is that it will need three pillars. First of all, we need to measure how much water is used. Something that farm is a very basic thing. It's very hard to imagine going towards efficiency without measuring, without enabling farmers to know how much water they are actually using, right? That's the first pillar. The second one is to be able to inform or advise farmers about how much water they should be using. So it's not enough to know how much you're using, that's absolutely essential, but you also, as a farmer, should know how much you should be using in order to be able to to optimize or make your usage more efficient. And finally, obviously, as economists, we also feel that we need incentives in order to not just know how much you are using and how much you should be using, but also to want to conserve water and want to adhere to these recommendations. Okay, so we need measurement, we need advisories, because I think it would be naive to think that farmers always know exactly how much water they should be applying from an agronomic perspective. And we need incentives to make them want to utilize that information in order to conserve water. The problem is that each one of these pillars faces a whole bunch of challenges. First of all, in terms of measurement, it's actually quite amazing that water meters are a very rare thing in the global irrigation landscape. Um, in a place like India, where our talks today are concentrated, it's hard. I've never seen a water meter installed in any irrigated field or on any well that I've ever seen, that I've ever visited. I think they are very, very rare species, so they're based virtually non-existent. Um, it's also hard to give farmers advisories because we don't have easy and cost-effective ways of figuring out how much water should be applied to a field. And I'll go back to that in a minute. And finally, we also know that pricing, water pricing, is very rare around the world, especially in developing countries. And it's also not so clear how to implement it. There are political costs, there are transaction costs. So a lot of challenges here. Every one of these three pillars faces a whole bunch of challenges, and I want to spend a few minutes on each of them, just discussing, going into a little more detail from our attempts to do it in the field, how these challenges look at the ground level. So I'm going to describe some insights from two pilot studies in India, one in Gujarat, one in Punjab. The one in Punjab was also supported by the IGC and is done in partnership with Thapa University, where what we did, we basically installed water meters with 100 farmers in Punjab. They mostly grow rice, and about 60 farmers in Gujarat, mostly growing cotton. These are some of the first installation of actual water meters that I'm aware of in India. And we also read those meters intensively throughout a season. Actually, in Punjab, it's been a couple of years. And so we have a lot of data that is interesting from the point of view of how farmers use water. But here I want to focus on the experience with the farmers in terms of what that entails. So let's start with the first pillar, which is the idea of measuring water use. That is, so we try to do it by actually installing water meters on these pumps, something that is very unfamiliar there. And we encountered a whole bunch of challenges regarding the performance, the technical performance of the meters and their installation, farmers' acceptance, and also accuracy in the sense of what we can learn from what we read in the water meters. Let me explain. First of all, water meters, I think, are more expensive than they need to be. The basic, most cheapest water meter that was completely mechanical will cost you around $100 US. If you want to move into something which is a little bit more, something that maybe is more robust, more precise, digital, can broadcast the data, you're going up to hundreds of dollars. I think there's a lot of room for improvements in the cost of simple water metering devices. Maybe more serious is the fact that they're kind of hard to maintain. In Gujarat, more than 20% during a course of a single study became clogged. So there are maintenance issues there that are not going to be possible for farmers to do on their own. And also, what we discovered in both Punjab, but especially Gujarat, is it's hard to fit these meters to the existing piping systems that are prevalent with these farmers. Often, these piping systems are ad hoc, somewhat informal, sometimes all kinds of makeshift things. So, and every pump is different. So it's actually quite challenging to find where to put the pump, where to place the meter and how to make sure all the connections work. Sometimes one end of the meter was open, sometimes water goes back into another pool. It's a mess. So quite often it was really challenging. It's not a cookie cutter thing about how to implement those meters, but that's a more technical issue. What about farmers' acceptance? Are they willing to install meters? Here we had varied experiences. In Gujarat, basically all the farmers we engaged were willing to install a water meter. But in Punjab, it was much tougher. Even when we offered a $25 incentive, only a quarter of the farmers that we approached actually agreed to install a water meter. Probably one reason is they might be suspicious about intentions to meter them and charge them eventually for the water, which is something that farmers oppose. Um, but maybe also they didn't see the value in that. In Gujarat, better success could be because we told them we'll provide advisories, or because we worked with an NGO that already had some relationship with the farmers, which means this might not be scalable. So there do seem that at least in some parts, acceptance is going to be, voluntary acceptance is going to be a challenge. And then one other issue that I want to mention is, even if you put a meter on a well, that may not be the same, and you meter the water going through the well, that may be different from the amount of water that's going to be applied in the field. There's a lot of leakage we found in almost 20% of our pipes. Many times wells are shared amongst different farmers. They channel water to different plots. You're not going to put a meter on every plot. That's going to really bring the costs up. And also, often the area that the area of the field is not exactly what the farmer believes it is to be, which impacts the accuracy in millimeters of how much water is actually being applied. So there's a whole bunch of issues. Especially salient one is the fact that often, if I am a farmer and I have a well, and I put a water meter on the well, sometimes water from my well is going to go to another field. So if I want to learn about how much water exactly goes into my field, this is going to be confounded by all these transfers of water between fields. Just to give you an example, here is one of our water meters, and what you see on the y-axis is the cube meter per acre on a day-to-day basis that is we metered actually. First of all, you see, and this is we actually took readings of the meter twice a week throughout the season. First of all, it's interesting to see. I mean, I think this is some of the first data on actual high frequency data on water use that we have in India at least. And you see, first of all, it's quite irregular. And what I want to point out here is this bump around day 80, which we think probably means that water went out of the farm to another some other farm on the same well. So if we try to calculate how much water is applied in the field itself, that's going to be a challenge. So these are the challenges that have to do with actual metering. Now let's move to the second part of it is, even if we have metering, how do we provide advisories? How do we tell farmers how much they should be irrigating? And here, the traditional approach are irrigation schedules that are determined by agronomists for many years. Some irrigation companies also provide them. You can see an example of that on the left-hand side, like a schematic, basically telling farmers how many days, after how many days they should apply their irrigation. These are kind of, pretty rigid schedules. They're often, the problem with these schedules is they are quite general. They also depend on the soil type, when the crop was sown, the crop variety, and they depend on the weather, obviously, because when it rains, you need to irrigate less. When it's hot, you need to irrigate more. So they're not customized and they're very generic. In our experience in the field, very farmers are even aware or use these. They mostly use rule of thumb approaches. A much more accurate approach, mostly in more high-income agriculture, is achieved through the use of sensors. Soil moisture sensors, usually a traditional approach, they read the moisture levels in the soil and then based on that you can calculate how much water should be applied. But also recently, in recent years, there's a whole industry of startups and innovations that also try to sense the water stress from the crop directly. Many innovations there. The problem is those things are pretty expensive. They're not really suitable for smallholder agriculture. One promising area has come in recent years, like in many other parts in agriculture, is to use remote sensing and the prevalence of mobile phones with farmers. There are companies that came up with ways to use remote sensing rather than in situ sensors in the field, to use remote sensing from satellites to figure out how much water a field needs, and then to transmit that information to the farmer's mobile phone through an app or even through SMS messages. So that has become a very promising, low-cost, cost-effective way to disseminate those recommendations. And we actually tried to see how those would work in Gujarat. And we encountered a very significant challenge that has to do with the sensitivity of these recommendations to things we don't know very well. So basically, the idea is that this algorithm that these companies present takes data from the satellite that sees the field and can sense how water stressed it is. Also takes data from whatever weather advisories are available locally, and some parameters about the crop, like when it was planted, the soil type, etc. Takes all these things, the algorithm, the black box calculates, produces the irrigation recommendations, and then sends them to the farmer's phone. What we found when we actually experimented with some of these companies, we found that we didn't have very clear-cut weather data for the specific area we were in. And when we changed the sources of the weather predictions or the actual weather observations, we found that they had a big impact on the recommendations. So that means if we're so sensitive to weather condition and we don't know the exact weather condition, in Gujarat, in India, it varies. So you don't know exactly, you don't get very spatially precise indicators of the weather. There's going to be all this uncertainty, and it means that the recommendation may not be very precise or reliable for farmers. Also, there are many parameters that you need to put into these algorithms, and farmers may not know them very well, which also increases all these variations. So I think for this to become more practical, what we need is products which are much simpler to interpret to the farmers in terms of what they should be doing, and more robust, less dependent on uncertain parameters. So I think there's a lot more that the industry needs to do there to make it viable for smallholder agriculture, despite the hype that is out there about that. And finally, when it comes to water pricing, this is a map from a paper that I'll mention later, Chakravorty et al. In Bangladesh, basically showing that pricing is still a big challenge for water. There's a lot of political resistance. Many places have social norms which against pricing of water being such a fundamental human need. And also there's issues where it's not clear how pricing water would impact the poorer farmers who often buy water in informal water markets. So there's a whole bunch of challenges there about pricing water, but this is well known. I wanted to focus on the things that we have discovered in the field. Now, in closing, before I close, and I guess I have to end in a couple of minutes, I want to quickly mention, so that we end on a high note, even though, first of all, we have encountered all these challenges in the more direct approach to achieving an efficient irrigation economy, it doesn't mean that it's hopeless. I think there's more work that can be done both on the technical side and on the institutional side to try to figure out how to do that. But it's also worth to think about alternative approaches. And in alternative approaches, there are two basic alternative approaches that don't try to meter and measure and pay for every drop of water. One is that instead of focusing on water, to focus on the electricity that is used to pump that water. That's not a one-to-one, it's not perfect, but I think it's an interesting approach. Nick will talk about this in detail after me. I want to talk about another approach which is less ambitious in trying to examine and measure every drop of water and to price every drop of water and to tell farmers exactly how much water they should need, but instead is based on promoting simpler and more heuristic water conserving practices, which are easier to monitor and easier to incentivize. So I'll skip over this part about the electricity pricing. I'll jump straight into this topic. So for example, if we have a water practice, we don't try to install a meter, we don't try to have the farmer pay per drop. Instead, we just choose practices that are known to conserve water and are simple to verify and observe and to practice for the farmers. And then we can give the farmer an incentive, flat incentive based on actually adhering to that practice. That can simplify a lot of the technicalities and the transaction costs that I described earlier. I want to give you an example of that in rice cultivation that we tried in Punjab. It's called alternative wetting and drying. It's a very well recognized approach to save water in rice cultivation. It is agronomically shown to save as much as 30%. And previous studies in Bangladesh and in India have found mixed results about whether farmers actually adopt and use this technology, depending when there is no pricing of water. The technique itself is pretty simple. You put a PVC pipe in the rice field, which enables farmers to see what the level of the water is in an easy way. And you tell farmers that they should not be going too high, and also that they should let the field dry before irrigating again. And agronomists in Erie have shown this saves about 30%. It's a very simple approach. And what we try to do in an ongoing randomized control trial in Punjab is to see whether actually providing farmers with this technology actually leads them to adopt it and save water, especially when they're not only, so in one of our treatment groups, we only provided training in how to use this thing, whereas another group, we actually offered an incentive based on the verification of whether they adhered to that limitation on the level of the water in the field. They got a flat payment every 2 weeks. Okay, and what we found was that, first of all, even though water is not priced and even electricity is not priced in Punjab, just training itself had a substantial impact on compliance with this technique. So what you see in the graph, the yellow is the control, and week by week, how many of the farmers complied with this practice. So in the control group, there is also some compliance. It goes up during the season because there is less irrigation required. But when we offer training, we also see some increase in compliance. But when we offered also the simple incentive, in addition to the training, we saw that the effect is almost doubled. So we see a pretty substantial increase in compliance as a result of the combination of the training and the incentive and the corresponding decrease in the level of the water. So these are just initial results. And of course, a big question is whether the amount of water that is actually saved justifies the payment. We're still working on that. But I think it shows that maybe there is scope here to be less ambitious in the kind of precision we hope to introduce into smallholder irrigation, at least in the short run, and maybe also start with things that are simpler to implement in terms of technicalities and transaction costs that may be second best, but can still constitute a valuable step forward. And Nick will tell us more about the electricity approach. So thanks a lot. I hope I didn't go too much over.
Thanks so much for that really interesting presentation, Ram. Next up, we'll hear from Nick Haggerty. Nick is an assistant professor in the Department of Agricultural Economics at Montana State University. His research studies how people respond to environmental change and how policy design can help people to better adapt. He focuses on water resources and agriculture in the Western United States and also in India, which we'll hear about shortly. Prior to Montana State, Nick earned a PhD in economics from MIT and completed a postdoc fellowship at UC Berkeley. I'll turn it over to Nick.
Thank you so much, Jenna. Yeah, thanks. Thanks for to everyone for having me here and for Ty for funding part of this project. Ram made it sound like I am the pricing person here when he completely neglected to mention that he had a big pilot project about a decade ago that our project very directly builds on. Um, so this was not, giving him credit here. This is not our original idea, but what we were, so we were able to introduce some direct price incentives for water and energy conservation and groundwater pumping. And sort of the difference is that Ram's team was working with an electric utility, which has a more direct pathway to impact, but when we were able to work with an NGO, it gave us more flexibility in terms of some of the things that we're able to learn from the project. So let me jump into it here. Um, uh, yeah, okay. So, if you're here, you probably have some familiarity with the groundwater problems. Groundwater has been central to the growth in agricultural productivity in India and a lot and around the world over the last century. But it also brings, but too much reliance on groundwater has brought some serious problems in a lot of the world's most productive areas. Depletion has been shown to, well, it leads to well failures, it raises pumping costs, it can threaten the viability of agriculture, even increase poverty. So, one possible solution is, we have like technological solutions, and then, another kind of like approach is economic solutions. So, we're focused on this idea of price incentives, and the kind of idea here is that water in much of India and in many places around the world, water used for irrigation is free. It's either there's sort of no entity sort of charging people to use the water, and if you provide anything for free, there's sort of like not a lot of motivation for any individual person not to use it wisely, right? There's sort of no like natural limit to it. But in a lot of contexts, including the one we're working in, the electricity used to pump the water is also essentially free. Is heavily subsidized, and it's usually farmers are usually either paying a fixed fee for the connection, um, or some very very small volumetric fee. But it's the point is that there's no sort of per unit incentive on either the water or the electricity that they're using there. So the textbook solution that we teach in every introductory economics classes to a situation like this is why don't you just charge a per unit fee on the use of these resources. It's sort of a natural solution that tends to work well across a whole lot of settings. As kind of, prices are kind of the foundation of our modern economic system. But if a government were to come in and introduce a new price for water in a setting where farmers hadn't previously been paying prices, that's a very unpopular policy. So, the idea, well, not our idea, but an idea out there has been, rather than charging farmers to use water, why don't we pay them not to use it? So pay them to conserve water. So this kind of approach still introduces the same kind of per unit price incentives, but but maybe it relies on rewards rather than penalties. So maybe that's sort of more politically appealing. And in this context, there's sort of a natural way that you could imagine this being implemented, which is through the electric utility. Right. So like the electric utility is still has to pay for the electricity that they're providing. So you could imagine that they might be willing to sort of buy farmers out of the electricity they're using in order to conserve some of that. So we wanted to know, how well does a program like this work, and how can it sort of best be designed? So we ran a randomized controlled trial of this basic idea of payments for groundwater conservation in Gujarat, in the western state of Gujarat in India, in the sort of central Saurashtra region. Um, uh, our participants were we had about 1,000 farming households. They're mostly smallholder farmers who are mostly growing cotton. And we did this during the main irrigation season of 2022 to 3. So the basic idea is that we installed meters on farmers' individual pumps. Um, they weren't previously metered. And then for a randomly selected subset of our participants, we offered them cash for reducing the amount of that they're pumping relative to a quantity that we tell them, right? So we're offering them cash for reduced pumping. How do we define reduced pumping? So we tell them this number that we call the benchmark. Let's say it's 40 hours. If we come back and the next month the meter says that they have pumped 35 hours, then that means that according to our program, they have conserved 5 hours. So that's the quantity that we're rewarding them for. Okay, so we do that and we make that offer in the treatment group, and then we just compare the treatment and control groups. Okay, so we're going to have three main takeaways from the results. One is that the price incentives work. They do in fact achieve conservation of water and energy in smallholder agriculture. Second, this particular model of conservation payments is practical and sort of within the realm of cost effectiveness for an electric utility. But then third, the details of how you design a program like this turned out to be really crucial to sort of the cost effectiveness and therefore viability of a program like this. Okay, so we yeah, and I'm gonna I'll tell you a little bit more about each of those results as we go here. So all participants in our study received this hours of use meter. We had professional electricians install this meter. So this meter is measuring the duration that the pump is on, right? So we also spent a long time piloting a range of different types of meters and had many of the same experiences with the water meters that Ram was describing. And so we ended up, even though we tested a bunch of other options, we ended up with using the exact same model of meter that Ram's team used in their previous study. It works because the duration that the pump is on does we can sort of, with a couple of other pieces of information, we can convert that to water or energy use. So then in the treatment group, we offered this conservation payments program. So for each farmer, we assigned them a benchmark. We told them what that benchmark is. And then when we come back the next month to read the meter, then we give them a payment if the amount that the meter shows that they pumped was less than that benchmark. How much do they get paid? They get paid a fixed price for every hour that they pumped below that benchmark. So this does involve, like, understanding the structure of this program. It does involve a little bit of like somewhat complicated arithmetic, and we wanted to make sure that people really understand exactly what the numbers translate to in terms of financial rewards. So we had this laminated sheet here that I'll keep moving we posted this laminated sheet next to the meter where we wrote in a bunch of example calculations, like if your meter reads this, then you'll get this payment. And then the payment. So then we ran this program for 3 months. So 3 cycles of reading the meters and dispersing payments. All right. So our first takeaway is that price incentives work, right? So price incentives are able to reduce, to achieve conservation of water and electricity in irrigated agriculture. When we look at just the pumping duration, so that's the amount of time that the pump was on, the treatment group we're offered these incentives, pumped 22% for 22% less time. They also used, when we convert that to energy use, they also used a similar proportion amount of less energy. The amount of conservation sort of grew over time within the span of our program. We sort of interpret this as increasing trust over the experiment. Probably in that first month, many people might have been skeptical for very good reason. This is a new and totally new program, new people coming into their community. But then after they saw the money in their bank accounts, then it seems like the amount of conservation increased. And I'll also point out that like this was just a 1 year within, or less than 1 year. The whole project was within the span of one irrigation season. We came in and started these incentives after they had already planted their crops. So I think it would be very reasonable to expect that in a longer term program, you would see even more conservation, as farmers would have a lot more ways that they could respond to this, not just through irrigation intensity, but also through what crops they're planting. And so then we also saw no change to the agricultural production. So we were able to look at a few satellite data based measures of crop yields, and we saw some pretty precise zero effects on all of those measures. So there are limitations to using measures like this, but the data that we have is consistent with the idea that conservation can be achieved without harm to agricultural production. All right. Our second takeaway is that conservation payments are sort of practical and nearly cost effective for an electric utility, which is sort of the most natural implementer in this setting. So we calculated the average cost of reducing electricity consumption through our program, this conservation programs. That's about 6.6 rupees per kilowatt hour. And that's right in between. That's a little bit higher than the average cost of electricity supply in our particular setting. It's less than the cost of electricity supply in another sort of northwestern state of India. So it's definitely within the realm of cost effectiveness. So what this suggests is that the program could roughly pay for itself just in electricity savings if it were implemented by the utility. And that's just considering the benefits from conserved electricity, not any of the other benefits to society from groundwater conservation itself. Okay. And so then our third takeaway is that the details of how you design a program like this really do matter. Right? So like that, I just told you the overall cost effectiveness for our program, but there's a lot of there are a lot of decision points of how you design this program. And so one point that we want to make is that the prices that you offer have to be high enough to change people's behavior. So in addition to randomizing whether people were in treatment or control, we also, within the treatment group, we randomized some of the parameters of this program. And so one of those aspects that we've randomized was the price. So we offered either 50 or 100 rupees per hour. And what we see is that the high price group achieved more than twice as much energy conservation, and therefore probably water too, as the low price group. Right, so there's sort of like increasing returns in conservation to the price. So I want to compare this to some of the previous experience that the other researchers have had. Even the low price, this 50 rupee price that we offered, even that was twice as high on average as Ram's previous project in North Gujarat. So that could be one of the one explanation for why their project found little conservation, whereas we found more conservation. our low price is still higher, but it's closer to another program, sort of an ongoing program in Punjab that was evaluated a couple of years ago. And then the second point we want to point out is about the benchmarks, right? So remember that the benchmarks that's the value against which we're rewarding the conservation. And the point here is that the benchmarks need to be strict or stringent enough to avoid wasting money in this program, right? So the problem is if your benchmark is too lenient, if it's too high, you're going to end up rewarding a lot of conservation that you're going to be defining conservation that would have happened anyway, right? So let's say that a farmer is going to pump 40 hours without the incentive, and then we come in and we tell them that their benchmark is 100 hours. So now we have 60 hours of what we could call non-additional conservation, right? That's conservation that we're paying for that conservation, but it would have happened anyway. So we didn't need the program or the incentives. We didn't need those payments to achieve that conservation. It's not really conservation. So the point is that we don't want the benchmarks to be too lenient. If what we did was we sort of set a benchmark formula in our across participants in our project, and then we randomly varied for some people. Some people got sort of more lenient benchmarks and relatively more stringent benchmarks relative to that initial formula. Within and sort of within that variation and in relative terms within our experiment, we found that the relatively more stringent benchmarks were much more additional, right? So most of the conservation we were paying for was in fact new conservation that wouldn't have happened anyway. And it was the program was much more cost effective in that group, right? And so, I think relating this to sort of what happens in a lot of programs like this, including many of the sort of ongoing programs that several states of India are developing around direct benefit transfer, the most common choice of benchmark is based on historical use, how much they were using in the past. And so what our evidence in this project suggests is that historical use is way too lenient. It's going to result in sort of wasting a lot of money in this program relative to the sort of the most cost-effective design that you could make. All right, so to sort of conclude, we our three takeaways that I told you about, where the price incentives work, is that's kind of a general, hopefully a general lesson. This particular structure of conservation payments, is sort of a practical and roughly cost-effective approach. But then the details of how we design that program are really important for designing them. So as I mentioned, there are several states that are sort of working on and have had small ongoing pilots, and they're continuing to try to expand and develop programs that they call them direct benefit transfer programs, but they have this exact same structure. It's just that they're implemented within within the electric utility. And this is so I think a lot of the sort of the details that I was talking about like the benchmarks and the price, those are really important for designing these kinds of programs. But you could also think about just be going beyond this particular structure of conservation payments and thinking more broadly about price incentives, how to introduce price incentives for groundwater conservation and smallholder agriculture. There are other ways that you could imagine doing this. So if it's too politically difficult to switch existing electric connections to pricing, you could at least introduce pricing for sort of new electric connections. And then there's also sort of an increasingly popular approach of providing farmers with solar-powered groundwater pumps. if you can connect those pumps to the electric grid and then allow farmers to sell excess electricity back to the grid, then that structure would sort of replicate the same sort of price incentives that we introduced in this project. So I think there are some very realistic and promising approaches to scaling, at least the basic idea of price incentives. So thanks.
Great. Thanks so much, Nick. We have a few minutes for questions. I see that someone does have their hand up. Unfortunately, we can't support verbal questions during this webinar, so I would just encourage everyone to write their questions in the Q&A feature of Zoom. I'll get us started. I want to go back to the measurement piece that Ram was talking about. Ram, you had a great quote. You said water meters are a rare species in your study context, and talked a bit about some of the technical and engineering issues as well as social issues in water meters. And Nick, it sounds like you had some experience with these water meters as well in your study. So I first I wanted to give Nick a chance to respond to Ram's point about using simple heuristics rather than water meters. And second, this is a really complex issue, and I'm curious how you think about layering these solutions that are both technological and economic. For instance, is there any overlap in your study area? Have you seen any cases where economic price incentives have been combined with some of the more technological focused solutions?
Um, yeah, so I guess I'll start because you asked about the water meters. The um, uh, oh, sorry. Can you what was can you repeat what was the question about the meters?
Just a chance to respond to Ram's point about simple heuristics
Oh yeah.
as a first step. Hopefully,
Um,
I'm getting that right, Ram.
Oh yeah, yeah. So I mean, like that sounds like a very promising approach. I think that like a lot of the, um, I mean, especially the idea of like combining the technology and the training with the price incentives. I mean, I would sort of endorse like Ram's overall framework um that he laid out with those those three different components. Um, I mean that approach of providing incentives for using a water conserving technology like that there's you can think of that as mapping onto a of this more direct volumetric pricing scheme. There would be other things that you would want to consider too in terms of like what if people switch crops or what if people change the area that they're cropping or what or maybe those are margins of adjustment that like aren't that might not be sort of covered or incentivized by like those are ways of conserving water that wouldn't be sort of incentivized by one of those simple heuristics, but I think it has a lot of this.
I just have to add that it's not like I know that these things will work or I have a strong opinion. All I was trying to say is I think it's worth experimenting with some of these things. Um, and even if we do find them to have an impact, the crucial question is whether the impact is justified by the size of the incentives. And also, I think in Nick's study, can we find a way to offer an incentive that um, both generates a substantial response and is cost effective to implement. And I think that finding that balance is tricky, but if we can find a way to achieve both together, like both to have make it cost effective for the implementer from a social point of view, but also to generate a large response. So I think that's the tricky balance to find in all of these approaches.
Yeah, and I was gonna add that I think on your question about these approaches interacting, there's a paper that the Chakraborty et al. Paper that Ram mentioned. It's a really nice paper that so I'll just really sort of repeat the main the result was that there is this technology. It was the same technology Ram's team is using, but there's this water saving technology. It was successful at conserving water only in the places where farmers were already facing marginal prices. So I think there's that framework is or that result is consistent with Ram's framework that like you need both of these things. You need both you need farmers to have ways of reducing their water consumption and that make sense for them um, and the price incentives in order to get both.
I would add one point on that I also love the Chakravarty paper, et al. Paper, but there is also conflicting evidence from Haryana where without any price incentive, farmers use this same technique to actually also reduce water. And we also found in Punjab that even in our arm, which only provided training, farmers were able to save water. So I think the jury is still out on whether this kind of things can have any impact even when there is no price. And along those lines, I think the idea that there is no incentive for farmers to save water in India is a bit simplistic. It's true that there is no price on water and there is no price on electricity. That doesn't mean that there is no incentive to use water more efficiently. For example, many farmers in many parts of India are constrained in terms of how much area they cultivate in terms of water. So in the dry seasons, most farmers do not cultivate their full all of their land in many parts of India because water is insufficient. So that creates an incentive right there. If I could use water more efficiently, I could expand the area that I cultivate. So there is an incentive even when there is no price incentive. Farmers also have to bear the cost of deepening their wells. So, I think the price is very important, and I think Nick's results are actually really encouraging about the possibility of this approach. But I don't think we should take it as a sweeping statement that there is no incentive to use water more efficiently. So that may explain why sometimes, even without pricing, we do see some response.
Great, thank you. We have a specific question in the chat from Leah on the project Ram you mentioned on alternative wetting and drying. She's curious if you can provide more information about the cost benefit of adopting AWD, especially considering what inputs of labor, water, and how yield changes. And then her second question is if you have any insights on why the trend is parallel in compliance for the control group. Do you have some insights on what's happening there? I think you are on mute, Rom, and hopefully we didn't lose you from internet
Sorry, I lost you for
connectivity.
a minute. I'm just reading Leah's question. Oh yeah, good. So um, on the first question, is there a cost benefit? So actually, the AWD thing is super cheap. It's really just a matter of the pipe. From the farmer's point of view, the costs are very cheap. It's a few dollars to get that PVC pipe. Let's say you have a few plots, you put one in each plot. Um, Obviously, if you're not paying for water, there are no benefits. The method is really is claimed to have no impact on yields. We still haven't collected yield data for the end line, so I don't know in our study, but according to ERIE, it should not affect yields in any way. So I think from a social point of view, I think it's pretty safe to say that if it does achieve a saving of 30% of water, that it's hard to imagine that it wouldn't be cost effective because the technology itself is very low cost. Um, The second question, you haven't said why the trend is parallel. Well, basically, what's happening is that, and this is also something that's really interesting, I think, in general, that water use is most intensive in the beginning of the season, at least for rice, and then it goes down. So as you go further into the season, more and more farmers are comply with the method, even unintentionally, just in terms of how they usually do their cultivation. There is less water required as you go into the more advanced stages of the season, and therefore farmers don't exceed the height limits on just with that's an additionality issue. So some of the control farmers already comply with the method, especially in the later part of the season. That's why that curve is going up. I hope I got your question correctly. There could be some spillovers, but not as far as we know. The treatment was separated in the villages, so it was not, they were not mixed in the same village. So we think the leakage is minimal. I hope I understood your question correctly.
Thanks, Ram. And Nick, we have a second question from Samyutka in the chat for you about the spatial distribution of your treatment and control and what you knew about the historical use of water in the farms that you were working with.
This spatial, so spatial distributions. So, I mean, the treatment and control groups were randomized. They're sort of randomized, not within, sort of not by geography, but just overall in the experiment. Um, so there's, I mean, like on average, there's going to be pretty um, similar geographic coverage of those two groups. I'm not if you're wondering about like the spillovers, if that's the motivation for the question, we thought about looking at how does water savings from one farmer affect a nearby farmer who might be in the control group. Um, all of our farmers are pretty far apart from each other, and this is an area where the geology doesn't sort of transmit the water differences very quickly. So that's not really or where we don't think that the spillovers are a very big deal here. And oh, and the second part, sorry, I keep forgetting the. Can you remind me of the second part?
Let's see.
I'm
They ask, do you know if they didn't just divert the water from elsewhere, given how ad hoc the arrangements are, as Ram mentioned?
Oh yeah. Oh, in terms of like sharing water between farmers. Yeah, yeah. So that's a really important sort of aspect of the situation, or of this context. Um, so what we did was we collected data at baseline on who was sort of sharing water with each other. So we knew for each of the people that we enrolled, we knew um, like a full list of like who else they had either given water to or received water from in the previous year. And in almost all cases, those were family members. So like think about like a set of brothers who own land all next to each other, and one of them has a pump, and then they're sharing the pump across all three of them. So um, we first like in or when we were enrolling people in the project, we made sure um, to exclude people that were in sort of like water sharing groups that were too big. So we limited them to like groups of 4 people, and then we um and then we like made sure that the entire cluster of water sharing people like were either like they were either all assigned to treatment or all to control. So um yeah, and like in a scaled up program, like these kinds of concerns wouldn't probably be such such an issue, because you would be sort of implementing the same incentive across everyone in a given area.
Great. Thank you. An elegant way to deal with that design issue. I think we are at time, so I will just thank Nick and Ram. These were amazing presentations and really fit together so well. So I'm really glad that we were able to highlight both of your work at the same time. Thank you for joining us. I hope everyone has a great day, and we'll be in touch soon with a recording.
Thanks, everyone.
Thank you.